Hopefully you can all see that screen. Going to give it a couple more minutes for more people to turn up. I apologise for the flickery screens. I don't seem to be able to stop it doing it. And in the meantime, Matt's just watching the Hitchhiker's Guide to the Galaxy while he waits, which is quite appropriate.
Utterly brilliant. And apparently you can get the whole thing in Polish on YouTube as well.
I'm not sure the jokes would necessarily carry over in Polish though. It's quite an English kind of humour, you know what I think?
Although, you know, spending the last 28 years in a bar, that's translatable, isn't it?
Could be.
Are we actually going to do coding?
I'll be showing some code. I might write some code for your pleasure if you like. I mean,
I love that everyone sits with their own laptop.
Yeah, for that matter, you know, if you want to do some coding while you're at it, feel free.
I've seen that we don't want to be engaged today.
Don't make me work today, my friends.
Okay.
No, because I said every time I 3 days to every time to present this, and then at the end I don't understand well because then the next time.
Well, let's make a start. So I did promise you that this would be PowerPoint light and code heavy. I may have lied a little bit.
That's sort of my question related.
Yeah, there's quite a lot of PowerPoint, but we'll whiz through it. It's just really there for to illustrate my point. But there's demos and stuff in the meantime, so I'm going to sit rather than stand. Not much point otherwise. Okay, so I call the session Spinning Plates and Juggling Chainsaws, and the reason why is very simple. It's because doing concurrent programming well is a bit like spinning plates or juggling chainsaws. So, when you're spinning plates, you have to revisit each one in time, make sure it's still spinning, it's not going to fall over, and know what it's doing. And when you're juggling chainsaws, you better get your rhythm right, or you're going to cut your hands off. Pretty much. And if you write threads and get it wrong, then you'll cut your hand off. So this is the TLDR for those that can't be asked to stay. So after this, you can leave if you like. So computers are generally good at doing one thing at a time. Okay, that's all computers can actually really do, unless you happen to have a computer with more than one core. Humans are good at doing multiple things at one time. We all do multiple things at one time all the time, within reason. But the interesting thing is, computers are very good at pretending to do multiple things at one time, looking like they're doing things simultaneously. Humans, on the other hand, are very bad at thinking in a multitasking manner, because most of what we do simultaneously, we do unconsciously, without actually thinking about it. If you had to stop and think about it, if you had to think about juggling, you'd probably drop all the balls. So concurrency and asynchrony are hard because as people, we don't tend to think that way. We tend to think straight through logically from one end to the other. And because it's hard, we generally try to avoid it, which is why, even though you probably have opportunities in your code to use parallel threads of execution to speed things up or improve your efficiency, you're probably not doing it because, let's face it, it's hard. As web developers, which most of us around the table would probably say we were, we largely can avoid multi-threading because, generally speaking, you program in what looks like a single-threaded environment. But whether you like it or not, all of our software lives in a multi-threaded world. The whole operating system is multi-threaded, IIS is multi-threaded, so on and so forth. You need to be aware of that because it does have impacts upon what you do. And a little concurrency and asynchrony in your code can go a long way. So that's the TLDR, that's what I'll be talking about. If you want the ultra short TLDR, it's this. If you're going to juggle chainsaws, learn how to do it properly or have replaceable arms.
What is the TLDR?
TLDR, too long, didn't read.
You've ever read it? If you've been on the internet, you don't feel it.
I can't seem to stop the flickering. It's really annoying, and I apologise, but hopefully it'll calm down a little bit later. Right, so this is what we're going to talk about today. 3 parts. History lesson, a little bit about how we got to the currently sort of multi-threaded, multitasking world we live in. Second part, which I've called Concurrency is Hard. Just some simple examples of where you need to do concurrent programming and what's hard about it. And then part 3, specifically threading and asynchrony in .NET. Less interesting for the Java guys, I know, but actually most of what I say about .NET applies pretty much equally to Java anyway, because it's essentially the same. I don't know about the asynchronous stuff in Java. Perhaps the Java guys can enlighten us later on. Okay, so, oops. Part 1 of history lesson. Let's rush through this fairly quickly. So in the beginning, computers were inherently single tasking. You might argue that they are now, except when you have multiple processors. But early micros, who's old enough in this room to remember computers? Microcomputers. Or early South African microcomputers, or yeah, okay. So not that many of you, but early microcomputers had no operating system at all. Okay, the program that was running had total control of the machine until it ended or chose to end. And if it hung or it didn't return control, then basically you were hosed. Programs existed solely as chunks of machine code in memory without any protection, any management, or any control. And multiple programs, very appropriate. Multiple programs could be in memory at any one time, but only one could ever actually be executing. And a program could therefore have one and only one flow of control. There was no such thing as simultaneous processing there. All programs that appear to be multitasking, therefore, like most games, were actually implementing their own code for managing and synchronizing their tasks, which, if you've ever actually written a game on a Spectrum, not easy at all. And as I said, in those days, men were real men, women were real women, and small green creatures from Alpha Centauri 4 were real small green creatures from Alpha Centauri 5. I know that's not an accurate quote. What?
That's pretty accurate, I think.
Yeah.
Saw it on YouTube. And the first real Windows multitasking operating system was called.
I think Xerox PARC might Xerox PARC might want to have some contest about that.
Not the end.
This was the first computer I ever owned. By today's standards, it's fantastic. It had a whole, wait for it, 1K of RAM. 1K. And it was run by a little Z80 processor that I believe run at something like 5 kilohertz. I mean, we're not even to actually probably megahertz, maybe. I don't know. But something ridiculously small like that. And yet, you could do real interesting things with it. Today, we're very spoilt. But as I said, it had no operating system. It had
on the top right, 16 kilobyte RAM for
massive add-on memory. Yes, and it was a real revelation. So just as an extra treat for you,
you could actually get a larger memory pack than that gave it 64K and as wide as the machine. So.
Right here is a web page I found. So this is an emulation of a ZX Spectrum, which was the next machine on from that, written in JavaScript. So this is an entire Z80 emulated in JavaScript with the operating system and everything else. And it is real. You can use it. So I can type. I'm trying to remember how this keyboard works. No. Somewhere here I'm going to find. No. Do you know what? This is going to get very tiresome very quickly. But somewhere we're going to find the. Do you know what? Sorry, I'm not even going to do it. Right. Instead, I'm going to select. Where's it gone? There you go. Right. So there's Elite running on the ZX Spectrum. That's the whole game. At this point, that program has complete control over the machine. There is no operating system. That prompt that you saw is basically the basic editor. And all it does is it has a couple of commands on it to load machine code into a location in RAM and then move the instruction pointer to that point in RAM, which kicks the program off. That's all. That's all it's got. So there's no protection. There's no management. Anything can do anything. Can stomp over anything. This is how the world used to be. I recommend JSPeccy, by the way, for an interesting experience. I have an emulator written in .NET as well, which I was going to show, but I can't make it compile. But there's a few around if you want to have a play with these sorts of things, and particularly if you weren't around at the time. Not looking at people in particular, but Callum. Then it's quite a revelation as to what your parents had to deal with. So let me close that and get back to the presentation. Whoops. There we go. So then came the operating system. So early OSs were mostly concerned with loading, scheduling, and managing tasks. So DOS, most of you will probably have used DOS or a DOS box at some point. CPM, these are both inherently single-tasked OSs. Okay, the OS manages the disk for you, it loads and runs programs, and then basically it gets out of the way, provides you with libraries you can call into, but other than that, it does nothing for you. This provides some degree of protection against rogue programs, for example, through hardware interrupts. So you can have a hardware interrupt that executes every so often. If a program is deadlocked, then you can at least dump out of it. And some limited degree of memory management started to appear. And your early attempts then at multitasking. Anyone familiar with the word TSR? Terminate and stay resident. So that's basically a program that the opposite operating system loads for you that does its thing, that terminates, but it stays in RAM so it can be invoked again later. But there's no real notion of concurrency, there's no notion of parallelism here. Anybody remember GEM on the Atari ST? Yeah, so this was, this looks a bit like the Mac used to look in those days. This pretends like it's doing many things at one time, but it really isn't. Everything's single tasking. If you move to a foreground process, the background process just stops running. And lo, the OS begat the scheduler. Okay, so the first multitasking OS has introduced the idea of a scheduler. A control program manages the execution of other programs that are running, and a memory manager that keeps track of what is where in memory and tries to prevent one task from stomping all over another's memory. So some idea of memory protection. So programs at this point become what we now call processes. And the real difference between a program and a process, in my opinion, is that processes are managed by the operating system rather than simply started and left to do their own thing. But at this time, and we're talking probably mid to late 80s, cooperative multitasking was the norm on micros. So your program gets called, it has complete control of the machine, it calls OS services to do what it needs to do, but it's got control until it relinquishes that control back to the scheduler. And if it doesn't hand control back to the scheduler, then it hangs up the whole OS. And although there were some limited things they could do to fix that, generally speaking, if a program went rogue, you had to reboot your machine. It was that simple. And Windows was like that all the way through till Windows 95. And Mac OS was like that all the way through till Mac OS 10, which I believe is the right name for it, isn't it? Anybody remember this? Got another treat for you. This is Oracle VirtualBox. So here's a DOS prompt. Right, DOS prompt, dead simple. Yay!
Oh, wow.
So here's Windows. And again, this is a multitasking OS, yes, but it is cooperatively multitask. So I can run a calendar. A lot of these programs don't work, by the way. I'm not entirely sure why. This is 3.11. Okay, so I run the clock. I can leave the clock down there and it ticks away. I can bring the calendar to the front and I can do stuff with the calendar, and the clock is still ticking. Yeah. So this is multitasking, but at the same time, if either of these two apps decides to hang up, then the whole OS is going to break. So that was the state of the art, probably as late as 1991. I remember how to get my. Indeed. And you can just end your Windows session. This, of course, is where I have to remember how I get my mouse back. Ah! This isn't good.
Try and control them all.
No, it's
Quick Google.
Yeah, can someone quickly Google that for me? Oracle VirtualBox release cursor. I was fairly sure it was right control and this, but it doesn't appear to be.
So you haven't got an Ethernet card adapter installed in Windows 3.
No, and I'm not going to do the rest of my demo from it either. But seriously, can somebody Google that because I am stuck.
Right control key. Does
Right control key.
that work?
Yeah. Brilliant. Callum saves the day, and not for the first time either. Let's power that off. Okay. So those are the fun bits done now. The rest of it's boring. So okay, don't cooperate, preempt. This is the next big step. Preemptive multitasking becomes the norm. Now we're all used to this. The idea is the scheduler allocates a time slice to a process, and when that time slice expires, the process is suspended. That requires the scheduler to have actual control of the process. Okay. So the way this was done was through hardware interrupts, and then later on specifically hardware threads. So Intel processors and the 386 upwards all support the idea of virtual machines that can be scheduled. A VM, not quite the same as like a Oracle VM box, but a virtual processor that can have a lifetime allocated to it and that will give control back when that's finished, when that time slice is run. So a rogue process can no longer handle the whole system under normal circumstances. I mean, we've all seen blue screens and stuff, and at this point you get the introduction of virtual memory management, virtual address spaces. Is everybody comfortable with what I mean by that? Or should I explain a little bit more? So if you go back to your Spectrum, which has a fantastic 48K of RAM, from the Spectrum's point of view, from a program's point of view, that's just a number of addresses from 0 to whatever 48K is. And it's one big block, and everything lives within it, and it has a place in that block, and that's the world as it sees it. In a properly memory managed operating system, every process sees a memory space, but that memory space is not real memory, it's virtual memory. It doesn't really exist. In the case of Windows, the virtual address space for any process is what used to be 2 gig. I think it's now 4 gig with Windows 10. But either way, this is a space of 2 or 4 or whatever gigabytes in size that, from the program's point of view, is completely empty apart from it and its data. In reality, real memory from your bank of RAM is mapped into that space in pages. Pages use like 64K in length, so there's lots of them. And they're mapped in, they're mapped out as the process needs it. And if a process is idle and the RAM is needed, then it will swap some of those memory pages out to disk and store them, and then give that memory over to another process to use. But from every processor's point of view, it's the only thing in the entire world. It's the only thing doing anything. And that is kind of the key to modern multitasking operating systems, understanding that everything is virtualized and that every process sees the world as if it's running on a spectrum, that it's the only thing running. The only way that it can actually share memory with another process is if it allocates a block and explicitly declares it as a shared block so that another process is allowed to touch it. And that's the way that early Windows programs used to communicate, through shared memory. It's obviously pretty dangerous, so now you don't do it anymore, but then, back in the days of DDE and stuff like that, it was the only way to do it. So now we thread it all together, okay? So originally the only unit of work was the process, just a single program doing whatever it does until it terminates. Threads came in later, and they were introduced as a way to multitask inside a single process space. And the main difference in a thread and a process is process has its own virtual address space, but all the threads in that process share the address space of the process with all the other threads, right? And that does make threads inherently dangerous because one thread can, in theory, stomp all over the memory that another thread is using. Now, there is some degree of protection built into Windows and other operating systems to stop you doing that, and in .NET it's not a problem because threads are fully managed. But threading is still inherently dangerous in the way that multiprocessing on modern operating systems is not. Okay, so they're dangerous only to the process in which they run. And other than that, they're scheduled just like processors are scheduled by the scheduler, and their memory is managed by the VMM. On modern CPUs, so on Intel CPUs, I think beyond about the Pentium, threads are now managed directly by the hardware in the same way that process VMs are managed. You probably heard the term hyperthreading. So some Intel processors have hyperthreading, which is a way to look like you're doing two things at once, when in reality it's two threads using a single core, and all that stuff's managed on the silicon now. So the implementation is much easier, but lower power CPUs, some of the earlier ARM CPUs, for example, still use software managed threads. So in the embedded space, it's very common to have OSs doing all their thread management in software. Okay, so that's the history lesson. So part 2, concurrency is hard. Why? Let's get our terminology right first of all. Okay, parallelism is where you split a task across multiple threads usually to improve performance. And the key thing is that the tasks are running simultaneously. Now, we know that on a single processor computer, that's not strictly true. They're not really running simultaneously, but they kind of look like they are. In a multiprocessor environment, and we're almost always in a multiprocessor environment now with multi-core chips, then when you split tasks up across threads, chances are they actually are running simultaneously. Okay, concurrency is where multiple threads have to interact with each other, and synchronization comes into play. But the key thing is that tasks are overlapping. So the threads may not be doing their work at the same actual moment of time, but they are overlapping with each other, and they have shared resources that have to be managed. And asynchrony is just where the flow of control is not synchronous. So things can happen in a different order than they were initiated. So one thing starts and carries on going whilst another thing then starts what it's doing, and so on and so forth. And then they return in an order. And the order may not be what you predict either. Parallelism and concurrency inherently involve working in multiple threads, whereas asynchrony does not always involve multiple threads. You might think, well, why not? Well, the answer is, particularly if you're using async in a way, quite often your asynchronous call is blocked on, like, say, I/O. So you're waiting for a file to be loaded or something like that. And in that case, what you're actually blocked is you're waiting for a signal back from the hardware. So in that case, processing will continue on the same thread, and then when the hardware signals, at that point, the thread will be interrupted and the work will continue from where it started. But that can all happen on a single thread without any need to have multiple threads involved. Nonetheless, you should always treat asynchronous cases like they are multi-threaded, and make sure that any resources you use are treated in a thread-safe manner. Okay. So simple parallelism is quite straightforward. Multiple threads do work, and eventually they end when the task or process ends. That assumes there are no shared resources, no information put into or taken out of threads except at the time the thread's created. So it's fire and forget, let it do its thing, don't care when it ends. It's easy, right? Everything else is hard. As soon as you have shared resources, any value or object more than one thread has to interact with, or you need to communicate with a running thread, put information into it, take information out of it, you have synchronization issues. If you're lucky enough that all of your data is read-only, then you have minimal synchronization issues. The moment you have to write things or change the values of things, or call stuff that changes things, then you have big issues. Because when a thread runs is controlled by the OS, not by you, you have no way of knowing when a given thread may touch your shared resource. Right? And it might happen in between two lines of code, which have to happen as a block. One needs to happen straight after the other, but another thread may have already jumped in. You can't control that. So you have to use the synchronization facilities that the framework gives you to keep these things synchronized. And this opens the door to two things called race conditions and deadlocks, which can break your code. And that's what I want to talk about next. Okay. Race conditions. So a race condition can occur when actions happen in a different order than that was expected due to the existence of multiple threads and shared resources. So the example, classical one, is this. Thread A, thread B, both need to access a shared variable, which we'll call total. Thread A increments total by 1, displays the value. Thread B decrements total by 1, displays the value. Thread B happens to get in and decrement the value after thread A has incremented the value, but before thread A displays the value, then the value that thread A displays is not what you would expect. Sometimes that's okay, but most of the time it probably isn't. You mitigate race conditions by using synchronized access to a shared resource. And in C#, the main way to do this is using the lock keyword, which is just a shorthand for monitor.enter and monitor.exit. There are a bunch of other synchronization primitives that exist. There's various things called mutexes, mutually exclusive locks. There are some synchronization primitives, things like spin locks and so forth. I'm not going to cover any of those. If you care enough to look into those things, all the documentation is available online, but they're all variations on a theme pretty much. Like you get locks that expire after a certain amount of time to try and avoid deadlocks and those sorts of things. But be aware that using locks can lead to deadlocks. And a deadlock occurs when two threads are waiting on a lock or a mutex or a semaphore. These are all the same thing basically to clear, but neither thread can complete the work because the other thread has locked a resource it requires access to. Okay, I'll show you some code that does this in a minute, so it'll become a bit clearer. But so in a bank transfer, we deduct from account A and we credit to account B. Both accounts have to be locked while this happens so that no one else can do anything, right? So thread A wants to deduct £5 from account A, credit it to B. At the same time, thread B wants to deduct £10 from account B and credit it to account A. Right? So thread A acquires a lock on account A and is just about to perform a lock on account B, but thread B has jumped in and locked account B. Right? Thread B now needs to lock account A, but it can't do that because thread A's got it locked. And thread A can't lock account B because thread B's got it locked. Neither thread can run. Everything grounds to a halt. let's have a look at that in action. So I've written some very contrived demos for this session. And we'll have a look at the race conditions and deadlock one first of all. Okay, first of all, can everybody read that? Shall I whack it up a bit? Can everybody read that now? Okay, again, sorry about the flickering. I can't seem to stop it. You'll notice for one thing, I'm using a lock object here. You'll see a lot of people when they lock doing locking on this for instances. It's generally discouraged for a number of reasons. But when you've got a static resource that you need to lock, you have no choice because there's no such thing as this for static. So you need some kind of object you can lock, and I'm using this later on. So I've created this thing called an account. Okay, account is simple and just looks like this. So account has a name, it has a balance, it has a credit and a debit method that's not synchronized, and it has a transfer method that's not in any way synchronized. And all the transfer does is debit from here and then credit to the destination account. Okay, so that's pretty straightforward and simple. So what I do in my race condition demo, which is here, is so I create a new thread. Thread equals new thread. Don't worry too much about how we do threads. I'll talk more about that in detail later. Give each a name so we can distinguish them, and then I start each of them. And I'm passing in a console color value just because I'm going to use that to color their output so you can see which thread is which. And then I'm going to artificially spin whilst the threads are alive, because normally this would return straight away because obviously it's on a separate thread. So I'm just going to artificially spin whilst they're running and do nothing because we just want to observe what's happening. Okay, and then this is the actual work, and this will be called by both threads, this thing. And all it does is it does 25 transactions, creates a random delay. The reason we're doing random delays is because we want to make it more likely that two threads will clash. Again, it's artificial, but because these threads would otherwise just be like that, the chance of them clashing quite small. You'll actually see that they tend not to clash very much because things are very fast, but you can't rely on that. Okay, and then it's just basically deducts £10, shows you what the balance is, add £10, show you what the balance is. So the balance should go up, down, it should stay the same all the time, right? And you'll see what happens. And then at the end of that, once it's turned 25 times, it just aborts that thread. All right? So we'll run that one first of all. So let me start that. This is where I need to make this a bit bigger for you. So why don't we... Big enough? Okay, so press key to begin the race condition demo. Now you may have already started to spot a pattern, but we'll scroll back up and look at the history of that. Okay, so thread A gets in, count balance is 1,000, deduct 10 is now 990, add 10 is back to 1,000. Thread A then runs again. Thread B hasn't run in yet because its delay has kept it from running. So thread B now jumps in. Oops. It does the same thing. Thread A does the same thing. And these all look fine, right? And in fact, they are all fine. And then eventually, I know it happened because I saw it here somewhere.
You need to have the colors mixed up.
It did definitely.
It did, yeah. Eventually, we should see green and yellow interleaved when the two threads were running at the same. There we go. Okay, so thread A gets in. It deducts £10. The balance is now 990. Thread B gets in. Oh, it's 990, which is not what it should be. Deducts 10. Now it's 980, and it adds £10 back, and now it's 990. And then thread A finally gets back in, adds 10. So in the end, we got what we expected. The balance is what we expected, but you can easily see how that would break in the real world, right? So that's a live example of a race condition. Then I've got a deadlock demo, and this was actually surprisingly hard to engineer, but I just need to comment this out and comment this back in. There we go. So my little deadlock demo, what that does, it's not dissimilar, but it creates two threads again. it starts the threads. It's giving it a deadlock params structure that I've created. This contains pointers to 2 accounts and a console color for it to output in, because you can only pass a single object value to a thread. So it can be anything, but a structure is quite an easy way to do it. Okay, so thread A, I'm passing it account A as account A and account B as account B. But for thread B, I'm passing account B as account A and account A as account B, right? So you can see that the situation I mentioned where one tries to deduct from the other account and the opposite is going to happen. And as soon as the 2 threads run at the same time, in theory, it should all break. Okay. And the implementation here is pretty similar. Obviously, you wouldn't do this stuff in the real world. It's all pretty noddy, but let's run it and see what happens. Right. This will take a variable amount of time. I don't know how long. In fact, it might not even work at all, but it probably will. Let's see. Oops. There you go. So it's now deadlocked. And there's no way out of that other than killing the process.
You said the locks can time out.
Yeah, if I'd actually put a synchronization around these things, I deliberately didn't to create the deadlock. But yeah, if I put a synchronization around with like a spin lock or a wait lock, then you could have it so that after a certain amount of time, the lock would just get dropped. But then you still got the problem of data corruption. So in reality, you just don't ever want to get into a deadlock situation. You want to lock your things in such a way that the 2 threads can never do that. But because it's a logical issue, you've got to watch out and understand that you've created a situation where that can happen. And invariably, it's where where you've got 2 different resources being locked. Quite often, you don't do that. So what I really should have done in my account object is I should have put a lock around it in the actual transfer method. But because you're looking for eventual consistency between account A and account B, you also need to do synchronization across the whole operation. Yeah. Which I didn't do because I was not a very good programmer, and hence I created a deadlock. So there's your deadlocks. Let's go back to the PowerPoint. All right, so let's get to the meat of it. Let's talk about threading and asynchrony specifically in .NET. Okay, sorry Java guys, but I say it's mostly the same from what I understand. So threading in .NET is done in software at the app domain level. Everyone familiar with an app domain? Everybody comfortable with what that is? All heard that term before? Sort of, yeah. So an app domain is a .NET structure that lives inside a .NET process. And you can have more than one app domain inside a single process. But it's like a kind of a .NET structure of management. It's the basic .NET structure of management. And all of your managed threads live inside an app domain and are controlled by the app domain. And the key thing here is that every .NET thread runs inside a Win32 hardware scheduled thread. Yes. But there is no direct correspondence between your .NET thread and your Win32 thread, right? Because more than one .NET thread can actually run in a single Win32 thread because the .NET framework is not stupid. It pulls threads, it aggregates threads, and it assigns them as it needs to. So you can't say I've created a thread and it has a direct correspondence with a Win32 thread. If you need in .NET to be able to create and control a Win32 thread, you're going to have to do it using unsafe code. You can't just create a managed thread and expect that will correspond one-to-one. It doesn't. Okay. So if you're looking in IIS, if you're looking in in Task Manager, and you're looking at the thread count of your worker pool, you're thinking, God, that's a lot of threads. The truth is that thread count doesn't necessarily represent what your .NET thread count is at all. Could be substantially higher, could even be lower, depending on how the thread pool expiry is working. So the key here is that .NET threads are managed, whereas Win32 threads are unmanaged, and it's the same distinction between managed and unmanaged code. Memory allocation is managed, execution lifetime is managed, all those things are managed by the runtime. Win32 threads are essentially scheduled on the processor, and bad things can happen. In a managed environment, it's very hard for bad things to happen. You can deadlock, which might break your process, but ultimately, you can't do any damage with it. It's a managed environment. The base thread API, which we all know, is system.threading, because everybody's used thread.sleep, right? Probably the only thing most people have used because it's just a convenient way of introducing a pause. But there's a whole lot more to thread than that. Okay, there's a .NET thread pool object. If you've used thread pool, anyone? .NET thread pool is there to simplify thread use. Before the task parallel library, which Matt is going to talk about in more detail in a future session, so I won't talk too much over the top of him. the thread pool was the simple and quick way to spin off a worker and do something, and not have to deal with managing your thread lifetimes and not have to worry with all that complicated synchronization stuff. And actually, there's a lot of methods available to you in the basic class library to do synchronization. A lot of stuff I didn't even know about, but there's an automatically thread safe method for incrementing values. It's a static method on one of the classes. I can't remember exactly. I was in my research. I found it. There's a lot of these things that nobody's ever heard about, and it's all in there. I'm sure if you're a systems programmer or working on the Microsoft team, you probably know all about them. But the majority of us, haven't had to care. Yeah. So generally, direct manipulation of threads is discouraged, and these days you're supposed to use the task parallel library because that's what it's for. So let's have a look at threading in .NET. Back to Visual Studio. So now I shall make this my starter project. So another little noddy demo. Very similar here. So I've got 3 types of threading involved. So I've got basic threading, I've got thread pool threading, and I've got task parallel library threading. Demo actually looks like this. So in your basic threading, we say, okay, we'll create a thread. So this is how you do it. You use a thread start. So the thread start is essentially, you have to have that, and basically it's a structure that encapsulates a pointer to the method that's going to do work. Obviously here I'm pointing at an actual void function that I've created. You could just give it a delegate or a lambda as long as it matches the signature, and the signature basically, it's either void and takes no parameters, or it's void and takes an object parameter, which is the payload for the thread. Okay. Then you create a thread saying thread equals new thread. There is, by the way, a thing called the parameterized thread start, which allows you to pass in, say, like an object parameter, which you need. You give a thread a name. This is not a Win32 thing; it's just a .NET thing, but it's quite handy because I want to be able to identify a thread when it's outputting something. And then you've got to call thread.start before it'll actually do anything. Okay. And then here I'm just keeping a reference to it because when I get callback later on, I'm going to want to do something about it. I need a reference to it. And the actual work is here in do basic thread work, so that's a little bit further down here. So that looks like this. So again, bog simple. Forever. Console right line, hello from me. And then it says press enter if you think you're hard enough to stop me. And then just so we can, I'm giving a thread sleep just so it looks like it's doing something. And then I'm catching here the thread abort exception. But the reason I'm doing that is simple. Ordinarily speaking, if an exception is raised on your thread, then the thread will just terminate. But there's a specific exception, thread abort exception, that is generated on your thread when you tell the thread to abort. Okay, so when you give the thread.abort command to the thread, then the thread abort exception is thrown, and gives you an opportunity to clean up any resources that you have and get out gracefully and safely. You can even actually, although it's bad behavior, call thread abort.reset and refuse to die. And if you do that, then you'll hang, and eventually the scheduler. And if you've ever had to shut down Windows and it said, a process is preventing Windows from shutting down, that's generally what's happened. A thread has got out of control and refused to die. Eventually, the scheduler will kill it, but there's a timeout that you have to go through before you do that. And of course, it dies in an unmanaged way, so your resources may get buggered up. So let's run that bit first. So I'm just going to put breakpoint on this time around. So press enter for the basic threading demo. I press enter. And then let's do this. There we go. Oops. Let's do that again. Right, there you go. Okay, so the thread I've spun off is just dropping that message onto the console every 2 seconds. Now at this point, control should have already returned back to the main method. I've deliberately put in that wait statement to make sure that it doesn't. But otherwise, we'll be seeing the prompt to do the next one now. When I press enter, however, that is then going to cause thread abort to be called. So press enter. and the thread abort exception got called. It dropped that message on the queue, and it's died. Okay, so that's a simple way. So now the thread pool demo. Right, so this is really simple. It's just this. Thread pool, queue user work item, do thread pool work. Do thread pool work again is just a void method that takes no parameters and does something. And the thread pool will take care of scheduling it for you. It will start it for you. It will terminate it for you when a thread becomes available. The thread pool has, I think, by default, up to 5,000 threads available at any one time. So you handed off all that control to the operating system. Don't need to care. There are relatively few disadvantages. The only thing is you don't get the kind of fine-grained control you might want in some circumstances. But 9 times out of 10, it's a perfectly good way of doing it. Till the task parallel library came along, it was the simplest, easiest way to do it. And also, it's properly managed, and hopefully nothing can go wrong. So here's my my thread pool work. Okay, lots of setting the console foreground color and setting it back. Just I want to be able to distinguish by color. But it just says hello from the thread. Gives you the managed thread ID because there is no name obviously with thread pools. Then it's going to, for 10 times, it's going to sleep for a second, remind you that it's still here, and then when it's done, it's finished, right? And it's going to do that in the background. So, I keep picking the wrong program. There you go. So we'll call this here, and then immediately control will come back. So if I put a breakpoint here, then that breakpoint will be tripped, but that thread will stop because all threads stop, but the thread will be running independently. You'll notice the next thing it does then is prompt you for the next demo and wait for the enter key to be pressed. So if I start it, so there's your basic thread, and that's the first one. So thread pool demo, press enter. Now this has already come up, and it tells you to ignore the other annoying thread. And in fact, I can start the next demo already. The other thread's still reminding us it's still here, and it's done. So the 2 threads are interleaving at that point. So thread pool, you just hand it off, fire and forget, don't worry about it. And then the TPL threading demo. So again, it's really straightforward. So I'm going to do 2 things in this demo. First of all, I'm going to show you the dead simple case, which is called the parallel for each. So there's a static class called parallel, and it has a method on it called for each. And basically what it says is give me an enumerable of anything, give me an action to do, and I will perform that action on a pool of threads that are synchronized. So instead of having to go through one to the other, end to end, provided you can parallelize it, you can. So it's a lot quicker. This is the sort of thing we can actually use in our code in lots of places where you're doing a long-running for each, where it could be parallelized. No reason why you shouldn't, and that includes in a web environment. There's no reason why you shouldn't, because all the threads are just controlled by the thread pool, so you don't have to worry about them going rogue or anything, and you can do things a lot quicker. So if you're slow, or it's taking a long time, or your web page is unresponsive because it's marshalling data, then if you parallelize it, things suddenly get an awful lot quicker.
And if you have trouble, it can limit the number of threads max parallel.
You can indeed. So all I'm doing here is I'm creating a set of messages. I'm cloning it. I'm not actually cloning it 4 times. I'm exponentially cloning it 4 times, which gives me quite a large basis. And then I'm calling this parallel for each on messages. There's a lambda, gets the message, just does console write line message, says which thread it's from, and then just sleeps. And again, the only reason I'm sleeping is so that you can see these things happening rather than all looking instantaneous. So you remember those lines of messages are appearing. So let's look at that in slightly more detail. So you see thread 10, 13, 14, 15. See how they tend to be bunching initially? And they still are, but then they're spreading out. So you've got no control over what order they're running in. I mean, you don't. If you need to have control of what order they run in, you don't want to be parallelizing it. But because I don't care, it really doesn't matter. The other thing you'll notice is that it doesn't always, I'm trying to find a good example of that, it doesn't always use another thread. The scheduler is clever. If it can run the same thing twice on the same thread in less time than it would take it to run 2 things on 2 separate threads, it will run the 2 things on the same thread, one after the other. it's always trying to get the best possible result for you. And TPL generally works on that principle. So I'm trying to find a classic example. And of course I can't. Yeah, I don't. I think you're right. Yeah, I'm sure it's there somewhere. Take my word for it, it does happen. Okay. And then lastly, using task itself. Now, how many of you have actually done anything with TPL or tasks other than Matt, who I know? Okay. So if you've had to use async or await, or you've seen code that uses async or await, or you've called a library that uses async or await, you know what task is. All the task really does is it encapsulates a task, a thing that's going to go off and do something, and then come back and either give you a return or not. So task of something tells you what the return type is going to be from that task. Task non-generic just means void. But either way, when you do anything like this, you have to play with a return task. So I create a task here of return type decimal called big number, and it takes a lambda, and the lambda is a block of code. Okay, so I've got a total here, which is a decimal. I'm going from 0 to int max value, which is quite big, 2.4 billion or thereabouts, and I'm adding that number to the total. Now, obviously, I'm going to massively over exceed the capacity of decimal at some point, so this will crash. The whole point is I wanted to create something that would just run for a long time. Okay, we start the task here, and then I'm just going to check the task status each time. I'm going to do that a maximum number of 10 times. If it ran to completion, I'm going to break. This will never happen, obviously. And then I'm going to call thread sleep, which, again, you don't. Actually, TPL has a method called task.delay, which does the same thing as thread.sleep, which I discovered a few minutes ago. And then basically did it complete or not. So this is basically giving it some time to complete, and if not, I'm giving up on it. So let's run that demo. Let that finish. Right, so press any key for the task demo. Here we go. So task status is running. Still running. It's going to get quite boring in a minute. Still running. I don't know what's going to happen first, whether the thread will abort or my 10 times check will abort. I suspect the thread will abort first. Decimal's quite big, but it's not that big. It's be interesting. I haven't run this bit before. It's the first time running this code. I literally finished the demo about 5 minutes before I came in here. 9. 2.4 billion signed. 10. Oh, alas. So there you go. It got the better of me. Obviously, eventually that task would come back. All right. So those are the three main ways of doing threading in .NET as it stands right now. And of those, task is what you're supposed to use. So parallel, fantastic. There's a parallel version of link called Plink, parallel link, which provides you with parallel equivalents of most of the link operators that we're familiar with. That's well worth investigating. And then the task library itself has all kinds of clever bits and pieces, but I shall leave that for Matt's talk when he shows us how we're using it. And I'm going to move on to the final point of my talk, which is about asynchrony. Okay. So in historical order, the three approaches to asynchrony in .NET are as follows. iAsync result. This is the earliest one. It came with .NET 1. You'll all have noticed that there are methods in the BCL that have both a normal version and then a whatever async version. You may have even used iAsync result at one point or another. But this was the fundamental way of doing asynchrony in .NET 1 and kind of .NET 2 as well. Then there was EAP, or event-driven asynchronous processing. I am not going to talk much about that because it's really complicated, takes ages to think about, and involves complex mucking about with events that you really don't want to do. So my advice to you is don't bother. It's old hat. unless you inherit code that needs to use it, you generally don't need to care. And then TAP, task-driven asynchronous processing. Now the recommended way of doing asynchronous processing in .NET uses the TPL, and since .NET 4.5 we've now got language keyword support for async and await, which again is based on TPL. So demo time again. Here's my Asynchrony demo. I'm just going to close these. There you go. So Asynchrony demo is one of each. No, one of two. Sorry, I didn't bother doing EAP. So I've got an iAsync result demo, and I've got an async and await demo, which uses the task parallel library. You'll notice I've got a little green line there. The reason for that is because it's noticed that use async and await is awaitable. It's async itself, and it's reminding me that I haven't chosen to await it, and thus bad things may happen. In reality, they won't, because I don't care at this point. Exactly. But you get the benefit inside, which is the bit that I'm actually going to care about. So here's the demo. So the first bit is use iAsync result. So what we're going to do here is we're going to read a file asynchronously. The file I've chosen is boot.wim, which you might notice is there's a large image from inside the Windows installer that contains all the driver files, because it's quite big. Still only takes about 3 seconds to load, mind you. Excuse me. I'm creating a file stream, and then file stream, not file, but file stream has a begin read method. Begin read indicates to me that it's an iAsync result way of doing things. So I begin read, I point it at my little byte buffer that I created there, which happens to be the exact right size of the file. I tell it to start at 0 bytes, read this many bytes, call me back here when it's done, and this is just an object that I can pass in, so I've passed in a meaningful name, and I get back an iAsync result. One of the things I can do with that is I can call result is completed to see whether or not the operation is completed yet. Now, obviously, in the real world, I'd bugger off and do something else. Here, I'm just going to sit and wait for it because, you know, I'm boring. But what it's going to do basically is going to keep writing not finished yet to the console until it's finished loading. And when it's finished loading, it's going to call me back down here, and it's going to say done reading file. And then I've got to call file.endRead, give it the result, and that tidies everything up at the other end. That's the iAsync result pattern in a nutshell. It's very simple, it's very easy, and it works very straightforwardly. So let us run it. There you go. I tried to find a file that would take a while to load, but it would be so large that it would occupy basically all my RAM, because my disk is very quick. So there's that. And then the async and await demo. So that looks a little bit different. Okay, so what I'm going to do here is I'm going to give it a bunch of URLs. I'm going to go through each of the URLs. I'm going to process that URL in an asynchronous manner. Whilst it's doing its job here, I'm then going to get on and do something else, which in reality is just writing some numbers to the screen. And then it's going to call me back, and I'm going to move on to the next one. And all it actually does here, and again, I put in a delay so we can watch it happen, is it gets the contents of the web page and it writes onto the screen how many bytes were in that web page. That's it. Okay. But, and excuse me, I'm losing my voice. Calling a web page takes a few seconds, so there's a delay involved. We've got time to do a significant amount of extra work whilst we're waiting. So let's run that. Right, async and await. Here we go. So control's already returned to the main function at this point. Meanwhile, the threads are doing what they're doing. So that stuff is happening whilst this is still loading in the background. Again, it's happening whilst this is loading in the background.
It's just how many? There is just one thread that is downloading all the sites, or
I suspect the same thread is being used over and over again. It's up to the TPL.
And why is not running? Is not running more than one thread and to be faster? You can't do.
Yeah, you could do that. You could parallelize it. That's not the point. This is not a parallel demo. This is an asynchronous demo. The key point, and it's not very clear here, which is why it's a crap demo. But the key point is this: I've marked this method as async. As an async method, this tells the framework that it's a method that I can await. All await is doing basically is saying, go away and do this. And if you can't do this quickly enough to do it synchronously, do it asynchronously, and I'll get on with something else while you're doing it. Yeah? So this bit is blocked on awaiting it, or rather this bit, sorry. That is awaiting it. If I tried to use that, I won't be able to because it doesn't come back until this is finished. But I can do this in the meantime because this has got nothing to do with that.
If you tried to access constant length, would it tell the process to hang until that thread returns?
Quite possibly. Should we try?
Sure.
Yeah.
Cool. Okay.
Yeah, I think it just works, but you don't get the benefit. You just need to wait. It goes out.
Yeah. See what it does. Genuine innovation in demos. I like it. It's doing. The point is, it is now doing it synchronously, because until this call's finished, it doesn't know this number until the call's finished. So, but you notice, okay, here's the interesting thing. This can run straight away, but this can't, because this has to wait for that to come back. And if I did, yeah, it's all about timing. If I had a slightly less contrived example, it might be a little bit more obvious what it's doing. At some point, we need to write some decent demos for this, I'll leave. Yeah, yeah, exactly. So you have to make sure the code that you write, that you're expecting to carry on with, is not dependent on any of the results of the awaited task.
There's many ways that you can turn your perceived parallel or asynchronous code into synchronous code by adding pick up variables or putting locks in every place.
Yes,
without realizing.
Absolutely. And you notice inside this loop here, I've got another example. I'm awaiting task.delay, which is the equivalent to thread.sleep, basically, but it's better for a number of reasons. So again, I could, in theory, put some more code that would run in the meantime. Actually, I think when you put task delay, it stops everything. But anyway, I found this stuff quite hard to get my head around. I couldn't honestly swear to you that I really, really get it fully.
Because what is about task.delay? You have already something that is running async.
Yes.
This delay is going on the main task, main process, and the one that running async has no effect on this task.delay.
Stopping.
Yeah.
It's stopping everything. It's stopping the actual. If I make
it's a good question.
Maybe I'm waiting.
It might be. The reason I did it was just because otherwise you don't see the numbers being written, which is it's just busy work to indicate that something's happening. Yeah, I think we can both agree this is not a great demo. Anyway.
Well, it shows doing something.
Yeah.
Good demo. It's a good demo.
I think the concept is
Yeah. It is. It is genuinely hard, and it does do your head. I'm much more comfortable with threading in general than I am with this stuff. And yeah, async and await are very interesting, but the basic the thing that started to crystallize for me is what this is about. So it's the difference between, I could say await. Now it will give me an error that says it can only be used with an async method. So then I have to make this return a task instead of void, because you can't return. You have to return a task of something from an async method. So at this point, I can now await. Now it will say it has the wrong signature. Okay, fine. So let's call this not main, and then we'll go static void main. and we'll say not main. Okay. What I like about that?
If no one looks at that data first and goes, yeah, that makes sense. I read it. It kind of does. It's just that if you have a weight or yeah, that's going to learn from it.
Right, so now that I've put a weight in there, this should no longer be true. So let's find out. So now the links to the web page should start to appear, but it should not say controllers returned. Did that just crash? Did I just crash?
The demo got the features around it.
It's possible. Oh, I know. Sorry, my fault. And here's a perfect example. This, of course, I'm not calling a wait, so it's returning immediately, so the program's terminating. This is why I need to put another one of these in, just to make it stop. Right, let's see. So, web page link should appear before it says controls returned, because I've awaited on it. There. So I changed the flow of control by using a wait, because I actually waited on the asynchronous operation at that point, whereas before it was returning control to me immediately. Does that make sense, Nicola?
Yes, it's hard to, but yes, it makes sense. And I think in Java we haven't something like that. Or there's something like a wait. I haven't seen.
You can't use promises and stuff like that.
Yeah,
We should do it.
Yeah.
We should do a poll. This is pretty something we should do. We should show Java it to us.
Yeah, that would be really cool. That would definitely be cool. Okay, we're slightly over time.
We invite you to this. You're so lucky.
So in a nutshell, why should you care? Okay, you're a web dev, threading doesn't really matter to me, and actually you're basically right. It's not entirely true though. Yes, in a controller on a page, you work on a single thread from the thread pool in IIS, right? As I said earlier, IIS is multi-threaded. Requests are services, well, I can't even spell serviced concurrently, not sequentially, unlike Node.js. Anybody want to stick up for Node.js? No? Good. So your code's always running in a multi-threaded environment, okay? The moment you declare anything as static in C#, you have to care about threads. Yeah, and we do that more often than we think. Because anything static, same value exists across the whole app domain. And when there are multiple threads running in the app domain, multiple threads can touch that thing. If it's read-only, it's fine. But as soon as it's writable, you have a synchronization issue. Hello. Yeah, that's the whole point. Yeah, that's exactly what that's. At that point, you have to care about it and lock it. And so quite often, I mean, I do this pattern quite often. I will lazy initialize a collection of something that's going to get referred to everywhere. And so I'll have it as a static property of a class. And then you need to lock it, do a null check. If it's null, get it, fix it, query it, whatever you have to do, then unlock it and return it. At that point, it's read-only. That's fine. But if it's then going to be writable, you have to synchronize all access to it. So yeah, static is interesting. There's a way in C#. There's an attribute called thread static. If you apply an attribute called thread static to a static something, what that means is that the value or the method is static only across that thread. So if there are like 10 instances of the not 10 instances, if there are 10 references in that thread, they'll all get the same value, but 10 references on a separate thread are going to get their own copy of that value, and it could be different.
I think it makes a difference when you have block objects, you make them static or not.
Yeah.
If you make them static, they start all threads.
Yes.
So they block.
Yeah. Yeah. Another classic example would be if you want to hold context. So you've got context for an operation like a request. You want the context to live for the entire length of the request. You could, of course, just put it in request items. But if you like doing it slightly clever and you want to do like mything.current, which is a fantastic API pattern that I recommend to everybody, .current, like HTTP request.current, then you can store that in a thread static unless you know you're running in a web environment, in which case you can't, because IIS uses a thread pool, and you may get threads being reused, and then you have another request would inherit the old context. So anyway, I've got code that does all this. I can show it all to you if you care about it. So if you use any async method using shared state, you have to care about threads. If you use TPL to spin up a task, you have to care about threads. And ultimately, as I pointed out, you could use threads to improve the performance of your app in lots of ways. So if there's a message to take away, it's this: multi-threading, it ain't that hard. Just contradicted my entire talk, right? Looks hard, looks like juggling chainsaws. Actually, not so much. Any questions? Please, yeah, please add.
There's number of concurrent objects that help you. We automatically deal with lock stuff, concurrent dictionary, concurrent key, etc. Those may come in useful if you find yourself getting some race conditions.
Where's the fun in not doing it manually? No, Andy's absolutely right. There's so much stuff in the framework that we generally don't know about for all these situations. And Microsoft has basically got you covered, and they always have had. But most people don't know about these things, so they end up manipulating the primitives and doing it the hard way. Yeah. So I encourage you all to look for these things and look up the whole topic of concurrent programming. It is very interesting. It does have relevance to what we do. Maybe not as much relevance as if we were doing systems development or games programming or something like that. But ultimately, it does have relevance to what we do. Matt is going to show us exactly what relevance it has to our existing code.
I don't know what I'm going to show you.
Okay, well,
You've been talking about that. It's amazing. Best talk ever.
Yeah, it will be the best. This is a mere precursor to that.
I was thinking it was going to be the other way around.
Yeah, but hopefully, I may have made things a little bit clearer for those that maybe weren't as au fait with threading in .NET and the whole topic in general. If this has stimulated any interest, please come and ask me any questions you might have. No, of course it isn't. It's awful, crappy demo.
Yeah, definitely.
Okay, I shall put the code on Stash then for you. I'll put the PowerPoint somewhere as well, and obviously the YouTube of this suitably edited will be available for consumption later on. And thank you to anybody who's actually stuck it out on the Hangout. You're very welcome. But we're out of time. But has anybody got any questions in the room they want to ask while we're here? Other than can I go for lunch now? Okay, so Andrew, I'm going to hold you to promise to do an equivalent session for Java. I'm very interested to see that.
I think there's range of topics, so but the API is quite different in Java. I'm impressed with this, and it'll be interesting to see how it starts.
Dan, do you want to do one for Python or?
No.
Sure.
Don't know Python very well. Okay.
Yeah, I mean, if anybody would like to do more on this topic or how it works in other languages, it's all quite interesting. Christopher the Mill. Have a think about it. Anyway, come talk to me if you want to. Plenty of resources available online. It's an interesting topic. I just thought, if anybody wants to come and play with spectrums with me, I'm going to be doing more of that. Thinking about doing a code dojo where we have to write our code in Spectrum Basic. So that could be interesting. All right. There's parallelism. Oh, okay. Oh, I want to find somebody that can come and do a demo on concurrency in Node.js. Shortest session ever. We don't do it. Yeah. Anyway, there you go. If there's no more questions, I'm basically done. So thanks very much. Goodbye to the internet.